as we revisit the fundamental theorem today, we're going to see how an integral can both be integrated and differentiated. You can go both directions. A function, you can find the antiderivative of a function. You can find the derivative of a function. You can do the same thing with an integral. You can find the antiderivative of an integral, and you can find the derivative of an integral, and we're going to do both. This is something you know already. This is the first part of the fundamental theorem of calculus, part one, part A, I guess. If you integrate f prime over the x-axis from bounds u to v, you get regular f with bounds u and v plugged back in and the subtraction. That is the fundamental theorem of calculus, and you should be able to write that or understand it in any format, right? If I gave it to you, if I said this from u to v, you should be able to, in notation, write what that is. So what is the antiderivative of lowercase g? So then it would be capital G, right? The antiderivative is, and then what gets plugged in first? V, right? Minus capital G of u. You should be able to do it if I gave you h double prime of x dx, also going from u to v. In symbols, you should be able to do that. What is the antiderivative of h double prime? H single prime, right? That's the antiderivative of v minus h single prime of u. You should be able to do that no matter what you're starting with. Okay, except I guess we haven't done that, right? We haven't done what's the antiderivative of a capital that's already a capital? I guess we could make it up. We could say it's a bolded capital or something like that. I don't know. We don't really do that. Okay. But you should be able to be very comfortable. That is the first part of the fundamental theorem of calculus. Now, the second part, part B, is what happens to those three parts. So if we consider them in three parts, the part on the left and the two subtracted parts on the right, what happens if you take the derivative of that back again? All right, so what happens if you take the derivative of this side and then also take the derivative of this piece and then also take the derivative of that piece? That's part B of the fundamental theorem of calculus, that the definition of an integral also has a corresponding derivative at the same time. So that's the next slide. See what happens to that. Well, let's think about that a second. Let's start with lowercase f of v. What is the derivative of lowercase f of v? F prime of v times chain rule. Very good, because now you're taking the derivative, which means, so the chain rule's applied to what, Allie?
The v.
The v. So then dv dx comes after that, right? And then minus, and then the derivative applied to lowercase f of u would be f prime of u times du dx, so the chain rule of that. So in other words, the derivative of something that has an integral so I want you to look at like what happened here. We've got an f prime here and an f prime here. Where else do you have an f prime? There's one other place, at the original equation, right? So what happens is when you take the derivative of an integral, nothing happens to the function. If it was an f prime, then it stays an f prime and an f prime. That is the fundamental theorem of calculus. It's as if the derivative notation and the integral notation cancel each other out. They negate each other. So nothing happens to the f prime because you're not, I mean, you could say, well, I integrated it and then I differentiated it. So it just ended up right back where it started again. I took one step forward, I took one step back, I ended up exactly where I was. So the f prime stays the same. And then the upper bounds, the v, shows up plugged in, but its derivative shows up after that as the chain rule. And then the u as your lower bound shows up in the subtraction, but it also shows up in the chain rule. It's the chain rule part that a lot of people forget. Okay, they just, when dealing with the derivative and an integral at the same time. So this is where what you have it, okay? The derivative of something that's defined as an integral is the original function with the bounds subtracted, but also the chain rule applied. Okay, so just notice, I'll highlight it maybe. F of x, or f, just maybe f, f. The function stays the same. And then v up here, v and v prime. And then u down here, and then u and u prime. It's the u prime part. So then the question is, what if either v or u are constant? What would happen then? What happens if v is constant? Say that again. Part of it will be the v prime. If v was constant, the v prime would be 0. If u was constant, the u prime would be 0, which is going to cancel out part of the equation, right? So, oops, I don't want that. If either bound is constant, then the respective chain rule derivative, or the corresponding chain rule derivative, will be 0. Now, could both bounds be constant? What would the derivative be if both bounds were constant?
0.
The whole thing would be 0. But why is that true? What if both bounds were constant? What would that mean geometrically? Like if it was 2 to 5 instead of 2 to x. What if it was 2 to 5? What would that mean geometrically? What does an integral mean geometrically? It means area. And it means the area going from 2 to 5, which is going to be a number because it has a beginning part and has an ending part, so it'll be a number. So the derivative of the number is going to be 0 again. So if both bounds are 0, both bounds are constant, the derivative is a slam dunk 0. If only one of the bounds is constant, then the derivative of that part of it is 0, but not the derivative of the other part, because that's still a variable. Because the area isn't closed. It's going from 2 to x, 2 to an unknown. So here's an example. If a was the bottom bound, then that means there really is an f of a here. It just happens that dA dx, it happens to be that is 0, which then cleans out that whole back half of the problem. So it's still technically there, but because it's 0, we can simplify and get rid of it. So the same would be true if the a, the constant, so it's only true if a is a constant number here. So typically in calculus, u's and v's are not constants. U's and v's typically represent something that's changing, a variable, whereas like a's and b's and c's tend to be constant values. All right, so let's just try it. Find the derivative of an integral of sine t dt if the bounds are going from pi to x. So this is the fundamental theorem of calculus where you've got both the derivative of the integral. So when that happens, the function remains unchanged. It's just sine. Because you could do the antiderivative, which would be negative sine, and then you're going to take the derivative of that, which takes you back to positive, negative cosine, and then you take the derivative of that, which takes you back to negative sine. So it's just going to, but then what gets plugged in first? X. And then times the chain rule, which is dx dx, minus sine with pi plugged in, and then the derivative of pi with respect to x. So I'm just showing all the steps here. So dx dx simplifies to 1, but d pi dx simplifies to 0 because it's a constant. And so the answer to this is simply sine of x. That's all that's left. All right, the next one. Find the derivative of a function that's defined as the integral from 1 to x squared of sine of t dt. So because I'm finding the derivative of something that's defined as the integral, I'll have sine. What gets plugged in first is the upper bound times the chain rule on the upper bound with respect to x minus sine of 1 times the chain rule of 1 with respect to x. So again, I'm showing you all the parts. We know that the last chain rule, the d1 dx, is going to automatically be 0. And the derivative of x squared with respect to x is 2x. So the answer is 2x sine of x squared in simplified terms. Now you guys are going to get, you'll be more efficient and faster at that. You don't have to show all the subtraction parts and everything. I'm just showing them to you right now, so we're going through it carefully. Okay, here's another one. If I didn't have this integral here, right, if this was just t sine t, how would I take the derivative of it? Product rule. Boy, the AB class is struggling with that. We've done product rule for almost a month now, and they still look at that, and they just want to take the derivative of t by itself and the derivative of sine by itself and put them together. So if we didn't have the integral, we'd be using the product rule. But because we have the integral, the derivative of it is just t sine t, or something times something, but then my bounds need to get plugged in. So my derivative is going to be 5 sine 5 times the chain rule of 5 with respect to x, right? So I'm plugging 5 in. So 5 sine 5 becomes a derivative of 5, minus, and then x sine x times the derivative of x, or the chain rule of x. So then when you simplify, we know that the derivative of 5 is 0, and the derivative of x is 1. So the answer to this simplifies to negative x sine of x. So on your homework and on your tests and quizzes, you don't have to do the subtraction part. If you can do that mentally and just jump right to the answer, that's fine. But I'm showing you why that is what it is. Any questions so far? Okay. Now, just to keep you honest, we want to be able to do both. You should be able to actually integrate an integral, and you should be able to differentiate an integral. You should be able to do both. Right? To integrate an integral, we're going to go through the process of finding the antiderivative. So the antiderivative is the natural log of the absolute value of 3t divided by the chain rule of 3 plus c going from 2x to 7. See, so that is the actual integral using an antiderivative. So the answer on that's going to be the natural log of 21 over 3, which doesn't reduce, minus the natural log of 6x over 3, which also doesn't reduce. What I could do is put them together like this, the 21 over 6x and the whole thing over 3. That would be legal with subtraction. Yeah?
Do you still have to put the 6x in absolute value?
I should. Because I don't know what x is. And so then I should here as well. So this can reduce to the natural log of 7 over 2x, the whole thing over 3. Okay, just reducing. So those are the only legal things you can do. So to integrate an integral, you need the antiderivative. To differentiate the integral, the function itself remains unchanged. So to differentiate, I'll do d dx applied to 2x to 7 of 1 over 3t dt. In that case, the 1 over 3t remains unchanged. And so it's 1 over 3 times 7 times the derivative of 7 with respect to x. So the derivatives are applied to the bounds part of it, not applied to the function itself. And then minus 1 over 3 times 2x times the derivative of 2x with respect to x. So I know that the derivative of 7 with respect to x is 0. And I know that the derivative of 2x with respect to x is 2. So this whole thing is going to simplify down to negative 1 over 3x. So you should be able to do both. You should be able to find an integral using the antiderivative because there's no derivative symbol in front of it. But then if you put the d dx in front of it, you should be able to know how that's going to how that's going to apply or implicate it. Any questions on that one? All right, and then you should be able to do some stuff with it. Find the tangent line. So you should be able to find the point, and you should be able to find the slope, which is going to require you to engage both ways with this integral. So the point means you're plugging 3 in, but be careful about where you're plugging 3 in. What are you plugging 3 in for? X, and where's x in the original equation? In the bounds. So you're not plugging 3 in for t, you're plugging 3 in for x. So it'll be the integral from 3 to 3/2 of 1 over 1 plus t squared dt. So to find the point, you actually do need to do the antiderivative. So my point will be 3 for x, and then my antiderivative is the inverse tangent of t plus c on bounds 3 to 3/2. Which will be the inverse tangent of 3/2 minus the inverse tangent of 3. which is going to turn into a decimal. So my point this time is going to be decimal value. So you guys don't have to worry about it. I got it for you in radian mode. Inverse tangent. All right, negative 0.266. All right, to find the slope, I'll need to apply the derivative to the original equation. And when I apply the derivative to the integral, the derivative is applying to the bounds. And so this would be 1 over 1 plus half x quantity squared times the derivative of half x with respect to x. So I'm plugging half x in, and I'm applying the chain rule to half x. And then minus 1 over 1 plus x squared times the derivative of x. So for the first derivative, chain rule, I know that's half. And for the second derivative, I know that's 1. So altogether, I'm looking at a slope that is 1/2 over 1 plus half x quantity squared minus 1 over 1 plus x squared. And I'm plugging 3 into that, right? I'm plugging 3 in for the x value. So that'll give me 1/2 over 1 plus 3/2 squared plus 1 over 1 plus 3 squared. I can use my calculator on that as well. Minus. I get 0.54. 0.054, sorry. All right, so using now your point and your slope, you should be able to write the tangent line. So y plus 0.266 equals 0.054 times x minus 3. So you should be fluent in doing old stuff with new techniques. You need to know when to use an antiderivative, when to use a derivative. Their most favorite way to ask you to do this is to give you a function defined as an antiderivative and then having you actually have to figure out the various things. All right, so given the p of x defined as the integral from x to a, they want you to figure all of that out. So p of x by definition, and again, these are definitions, is going to be capital F with x plugged in minus capital F of a. So you'll need to know the antiderivative from x to a, which translates into the area under f of x from a to x. Okay, so you should understand both the, hi.
Calculus?
Yes. Okay, sorry. Oh, yeah. Thanks. Oh. Once I pause it, I can't go back and erase it, so just fix it. All right, then we want velocity to to be the derivative, so it would be d dx of a to x of f of t, which just kind of works to cancel things out. So we just have f with the upper bound of x plugged in minus f with the lower bound of a plugged in and the derivative. And this is where one of them has a derivative of 0 because it's a constant, and the other has a derivative of 1, which means all you're left with is just f of x. So what does that mean about, what are you looking for on the graph for velocity? Not here. Velocity is defined as f of x. So what's f of x? It's just the y value of the point. All right, so that is simply the y value on f of x. That's what we're looking for. So we're used to velocity being slope, but this is defined differently. They love to do this, is to define the original function differently, which means velocity is defined differently, so you're looking at something else to get the velocity. And then acceleration would be the derivative of what you just got. And so since I just got f of x for velocity, then acceleration will be, so acceleration based on time of t is going to be f prime of the position of x, which means we're looking at the slope value. So things are defined differently. The area, the position would be the area under the graph. The velocity would simply be the y value of the graph. And now the acceleration would be the slope value of the graph, where in the past, position was the y value, and velocity was the slope value, and area was the concavity. Now everything's different, defined differently. So you're going to have to trust your definitions and your understanding of what each of those means.